Good morning, good afternoon, and good evening to everybody. Again, thanks for being here for this second lecture after the kind of longer computational first one, full of proofs. Okay, so let me just recall what we did yesterday, and then maybe we can move to the second part, which takes into account non-local operators, and we'll try to see whether a theorem like the one proposed by Malmheden may hold true, and in which form may hold true in the non-local setting. So let me just recall. So essentially, all the proof that I gave yesterday can be found more or less in the draft of this book, Elliptic PDEs from an Elementary Viewpoint. So if I missed any detail, or I was not clear enough and you want to find out, I think there's a section dedicated to insight, so geometric insight on harmonic functions, which deals exactly with the Malmheden theorem. Okay, so as you see, there is essentially one paper here listed in this list of references where there is the word fractional. So today we'll see what this word means, basically, and then we'll see where we can get. Probably I will speak about the fractional Malmheden theorem tomorrow, and today I will just give an overview of, so I will tell you what fractional means, and I will somehow describe some features of fractional and non-local equations. So yesterday, so let me recall. So yesterday we recalled the mean value theorem for harmonic functions. We said that harmonic functions are characterized by the mean value theorem. We gave the proof, and we also discussed about Courant theorem, which somehow is a characterization now not of the functions but of the domains where the mean value formula holds true. So we said that if I have an open domain, an open subset of Rn containing the origin and with the property that every harmonic function satisfies a mean value formula, then omega is to be a ball. So somehow the mean value formula characterizes balls, essentially. So we will see also what happens in the non-local setting to this theorem. So we gave the proof, somehow simple and clever proof of this result. And then we discussed about Malmheden theorem. So with this geometric construction where we have a ball, we fix the origin here, we take any point P, we pick any direction E, and we consider the straight line passing through P in this direction, and we take the two endpoints, which are the intersections between this straight line and the ball, and these points are called Q plus and Q minus. And then if one takes the affine function that somehow interpolates these two endpoints, so the value of the boundary value of f at these two endpoints, and we evaluate this affine function at P, then if we define UP to be the average over the boundary of B1 of this affine function, then Malmeden's theorem tells us that this is exactly the solution of the Dirichlet problem in the ball. And we proved this. I mean, the proof, if you remember, was a bit long in computation, but there were, I think, also some clever ideas here and there. And so we gave the proof of this yesterday. And the idea of the proof was, again, okay, start with this expression of the function, and I try to recover the expression of essentially the harmonic function using the Poisson kernel. So the idea was to do a bit of a clever change of variables and clever algebraic manipulations to end up here with the Poisson kernel against the function. So this was the idea. Okay, so this was the proof. very long. If you remember, we had to compute the determinant of a big matrix. And then a particular case of Malmheden theorem was Schwarz theorem, just in dimension 2. So in this setting, the situation was slightly, I mean, at least the notation was slightly different, because one has, again, to pick up a point P. So now we are just in the plane. So the picture is a real picture now. So I have a disk in the plane. So I take a point P. I fix any point y along the boundary of P1, and then I take the straight line passing through P and y, and then Qy is the other endpoint of this straight line on the boundary of it. And then in this setting, Schwarz theorem tells us that if I define UP to be now the average over the boundary of P1 of f evaluated with Q omega, then again, this is the solution of the Dirichlet problem in the ball. And one can derive this problem, this theorem, simply using Malmheden theorem. So one can actually check that this expression here, which is slightly different from the one in Malmeden's theorem, it is exactly after some, again, after some clever change of variable, is exactly the expression that Malmeden had in this theorem. So one can derive Schwarz by Malmeden, though chronologically speaking, Schwarz theorem came before Malmeden theorem, and Schwarz proved it using complex analysis. So it didn't derive it, of course, from Malmeden theorem. Okay, so we also saw this nice application if you want to evaluate the temperature of a plate, knowing the temperature along the boundary. You can simply use Schwarz theorem and you're essentially done. And yeah, we also stress that Schwarz theorem only holds in the plane, because in higher dimension we had a counterexample. And so we finished essentially here, so with the proof of Schwarz theorem. So this is what we did yesterday. Okay, so now once we discovered this theorem, both Malmeden and Schwarz, we analyzed this. With Enrico, we thought, okay, because we were writing this book, so we're focused on this book, so just on harmonic functions, so everything local. But we thought, okay, since there is a fractional mean value formula that we will see, I'm not sure if we will see it today, maybe end of today's lecture or maybe tomorrow. So maybe there is also a fractional version of Malmeden theorem. So we'll start investigating this direction together with Giovanni Giacomin, who is a PhD student here at UWA. But before giving you the fractional version of Schwarz and Malmeden theorems, let me introduce you to this non-local world. So I'm going to talk about essentially a specific operator in the class of non-local operators, that is the fractional Laplacian. So that's the prototype example of non-local operator that we want to have in mind, and this is what we will be dealing with during this course. So, but before defining the fractional Laplacian and presenting some of the nice properties that the fractional Laplacian has, some of which are somehow the non-local counterpart of classical result in the local setting, and some of which instead are kind of different and surprising. So before diving into that, let me define the fractional Laplacian. Okay, so if you say I start actually with what is the Laplacian, because before defining the fractional Laplacian, I want to take a step back. So we gave a definition of the Laplacian in the first slide. I mean, the one that everybody knows. So the Laplacian is the sum of second order derivatives along the coordinate directions. So that's pretty easy, and it's easy to compute the Laplacian of a function with just state derivatives, so kind of easy. But okay, there are other definitions also of the Laplacian that one can give. For instance, the one that uses the Fourier transform, right? So the operation of taking essentially two derivatives to the Laplacian is equivalent to the multiplication by the symbol psi squared in the frequency space. And so if I take the Fourier, if I define, if f, this mathcal f, is the Fourier transform of a function, I know that I can write the function u okay, if U is reasonably good, U can be written in terms of its Fourier transform. So U is essentially the integral over Rn of the Fourier transform of U at xi multiplied by this exponential. Okay, so and this is something that, I mean, we learn at university, we study, and we know it. Okay, and so with this, so this is already okay. So with this, we can take a derivative. We can take a first derivative. So of course, I take a derivative in x, so in xj, where j goes from 1 to n. And then the derivative of u will be the integral over Rn of the Fourier transform, and then I have to take the derivative of the exponential, which gives me I, so the imaginary number, the imaginary unit multiplied by xij. And then I can take a second derivative, and I do the same again. So I will have another I xij popping up here. So I will have just minus coming from I squared and then xij squared. And then if I sum them up, I see that the Laplacian is exactly the anti-Fourier transform of this function here. So the sum in J of this function here, which is essentially the norm of psi squared multiplied by the Fourier transform of U. So this is a kind of ugly, if you like, way of defining the operation of taking two derivatives. So the Laplacian is the anti-Fourier transform of psi squared multiplied by the Fourier transform of U. And already this is a bit weird to me, because if you think about the Fourier transform is a non-local operator, in the sense that if you want to compute the Fourier transform of a function U, you need to know the value of the function everywhere. We are taking an integral over Rn. So it's a non-local operator in this sense. You need to know the big picture. It's not enough to know U at a given point. But then, if the symbol is psi squared, and then you take the anti-Fourier transform, you have nice cancellations, and this operator at the end of the day is really just the Laplacian, so a local operator, sum of second derivatives. Okay, but there is another definition, which in my opinion is even a better way to look at the Laplacian, which again looks like some kind of non-local operator, which is comparing with local average. So when we were proving yesterday the mean value formula, at some point I told you, I think we were proving that 3 implies 1, so that the mean value formula with volume average implies that the Laplacian is equal to 0, that the U is harmonic. We basically proved that the Laplacian of U can be written as the limit of some kind of non-local operator here. So this is non-local in the sense that, okay, if I want to compute this object here at x, I need to know the function U at least in a small neighborhood of x. So in a sense, it's some kind, it's not too much non-local, but it is some kind of non-local operator. And this operation, again, gives me the Laplacian. And if you remember, we proved this essentially by taking by starting from here and taking a Taylor expansion around x and exploiting cancellations and simplifications. And the constancy again can be written explicitly. So, so again, this is, okay, it's not obvious that it is a better way to look at the Laplacian, because of course, if I have a function and I want to compute the Laplacian, I don't want to use this definition. I don't want to use the Fourier transform either, because it may get complicated. But it's very easy taking derivatives, so I will do that. I will do that. But if I really want to understand something more about the harmonic functions, and if I want to understand why also the fractional Laplacian is defined in a given way, I think this is a better way to look at the Laplacian. Because here I'm really saying that Laplacian of U equal to 0 means that this object has to be equal to 0, which means that my function U around a certain point x has to be very close to that point, so to the value at the point x. So around my point, my function U wants to stay close, which is what essentially what happens when, if you take like an elastic membrane, every point will try to stay close to the others. And so this behavior is somehow encoded in this definition, so which I have to say I like a lot. And so once we have this definition, so you see I have also like somehow this 1 over r to the power n plus 2, we will see in the definition of the fractional Laplacian the role that is played by this object, so at least the comparison. So it allows us to have a nice comparison with the definition. Okay, so what is the definition now of the fractional Laplacian? Okay, let me take a nice function u. So nice means that I can take the operation that I'm taking. So it is so this object that I'm going to define is well defined. It is finite. Define it now in Rn to r, and I fix a fractional parameter s in between 0 and 1, and then I will define the fractional Laplacian of order s of u at a given point x in Rn to be exactly this operator. So it's 1/2. If you don't like this 1/2, you can remove it. I mean, there's also a constant here depending on n and s that I am omitting, because I will not take limits and stuff like that. So in this situation. And then I have, if you see, I have something a bit ugly at the first glance, because I have somehow a second order, it's a second order increment here. So you have like 2 u of x, and then I have minus u of x plus y minus u of x minus y. So it's a kind of second order increment divided by y to the power n plus 2s. And of course you can put together, I mean, you can separate ux plus y from u of x minus y and take one of these u of x together with the u of x plus y and the other one with u of x minus y. And then you can change variable in the integral with u of x minus y. So we can change y into minus y or minus y into y. And then you will see that it's exactly twice u of x minus u of y divided by the same kernel, essentially. If I do like this, I have to write it in the principal value sense. So I have to, because this may be singular now. So I have to remove a ball centered at x. So this is the definition of principal value. So I have to exploit cancellations hidden here. So that's the meaning of the principal value here. And now maybe you can understand why I introduced, and I like the last definition that I gave of the Laplacian, because if you see, this is very similar to this one here, right? So here I have 1 over r to the power n plus 2. Here I have, okay, inside the integral I have 1 over y to the n plus 2s. So when s is equal to 1, this is exactly y to the n plus 2. And yeah, so here I have some kind of increment. So I have u of x minus u of y, and here it's the same. It's just that here it's written in terms of second order. Here it's exactly the same. So they are very similar. The difference is that, so here I'm averaging just over a ball around the point. Here I'm really averaging over a Rn. So I'm taking an incremental quotient of order 2s, essentially, because it's y to the power n dimensionally should cancel the volume element. So I have a second, an incremental quotient of order 2s in this case, and not of order 2, like I would do it for the Laplacian. The difference with the Laplacian, again, is that I'm not just integrating over just one ball, but over a Rn. So I really need to know the function in a Rn, so everywhere. And so, in a sense, the fractional Laplacian will be even a more democratic operator than the Laplacian, because the Laplacian doesn't like oscillation close by, like close to the point, while the fractional Laplacian doesn't like oscillations everywhere. Okay, points that are very far away, maybe interact a bit less, because of course I have a kernel which is a polynomially decaying kernel, but still this operator doesn't like much oscillation. So in this sense, it's similar to the Laplacian, and it's even better in some sense. And then also in comparison with the Laplacian, we can also give another definition using Fourier transform again. And as you can imagine, instead of putting the symbol psi to the power 2 here, I will have to put the symbol psi to the power 2s. That's 2s is the order of my operator now. So as you can see, also the fractional Laplacian, so both the Laplacian and the fractional Laplacian can be written in terms of non-local operators, like the Fourier transform, using their own symbols. But in a sense, in the local setting, so when you have psi to the power 2 here, the Fourier transform has a nice cancellation for which, at the end of the day, this operator is not really non-local, but it is a Laplacian, so it's a local operator. So you really just need to know the function around the point if you want to compute it. But if you change the symbol to something like psi to the power 2s, then you don't see again all these cancellations that make your operator at the end of the day local. So it remains a non-local operator, which is something of this type. So again, let me stress, this is a non-local now diffusive operator. And again, it's non-local because if I want to compute the function somewhere, I need to know the function everywhere. And even if I change the function, so if I want to compute the fractional Laplacian at a given point here, even if I change the function far away, this modification will be seen, will be perceived by the integral, so the fractional Laplacian will change. And this does not happen for the Laplacian. If I change the function far away, the Laplacian will stay the same at this point. So this is a non-local diffusive operator. Okay. And yeah, so as I was saying before, like the classical Laplacian does, also the fractional Laplacian tries to average out oscillations. But differently from the classical Laplacian, the fractional Laplacian takes into account the global behavior of the function. Okay. Oh, let me point out another difference with, since we are here and we have the definition, let me point out another difference between the fractional Laplacian and the Laplacian. So the Laplacian, okay, so they both can be written in terms somehow of averaging in integrals or in terms of Fourier transforms, but then the Laplacian can be also written in terms of sum of second derivatives along different directions, along the coordinate directions. So one may wonder whether possibly also the fractional Laplacian can be actually written in terms of sum of fractional Laplacians along the coordinate directions. So instead of writing one integral in dimension n, which is Rn, I can maybe write the sum of fractional Laplacians along the coordinate direction. So this will be the sum somehow of n different fractional Laplacians in one dimension, seeing the function just along the coordinate directions. But as you can see, I mean, I can well define an operator of this type, like sum of fractional Laplacians along the n direction, but it's a different operator than this fractional Laplacian that I'm defining here. Because, for instance, let's think about dimension 2. So let me take, I don't know, a function that is compactly supported in one quadrant. So let me check here. Let's see if I can make it. So I have my coordinate axis, x1 and x2, okay, just in dimension 2. And then I take a function, I don't know, some function phi that is, for instance, supported in the first quadrant, just here. And then it's 0 outside a given ball contained in the first quadrant here, right? So now, of course, if I try to compute, for instance, the fractional Laplacian at 0, or I don't know, along one of these coordinate directions, so at x2 equal to 0, x1 equal to 0, this fractional Laplacian here that I defined today would see this bump. So the fractional Laplacian would not be 0, and one can check that because it would see this object here. But if I compute, for instance, the fractional Laplacian along this direction, then here the function u is 0. So that would be 0. And again, the same here, the fractional Laplacian along this direction would be again 0. So the sum of the two would be 0, while the fractional Laplacian that I defined today in Rn, in R2, would not be 0. So they are different. So I can't So this was not obvious in the beginning, at least to me, when I got acquainted of this object. But it is true that they are different operators. So you are perfectly fine if you want to consider the other one, like the sum of fractional Laplacians in different directions, but they are different operators with different regularity properties. So the fractional Laplacian can't be split into coordinate directions. You really have to look at the function everywhere if you want to compute. It's an integral over Rn. Okay, so yes, so if the fractional Laplacian takes into account the global behavior of the functions, you can't like dismiss the function somewhere because you are bothered by the bump or something. Okay, so why one cares about an object of this type? Well, there is a strong interest both from the theoretical point of view in terms of course, fractional calculus, singular integrals, and pseudo-differential operators and harmonic analysis. But there are also many concrete situations in which this object naturally arises, and I've got a list here. I won't talk about all of this today, or at least during this course, because that's another story. So for instance, in finance, if you think about the Black-Scholes model, you may think, for instance, that the underlying option as a cost, as a price that varies with a polynomial tail rather than exponential. So that would involve the fractional Laplacian in your model instead of the Laplacian. Engineering, for instance, if you think about the famous Signorini problem, which is an obstacle problem where you don't have, so for instance, in Rn you don't have an n-dimensional obstacle, but you put an n-1 dimensional obstacle, so thin obstacle, it's so-called thin obstacle. Then you want to understand what happens to the function with this thin obstacle. So that would give rise to the fractional Laplacian instead of the Laplacian. And it's named after Signorini, who was an engineer. So that was a problem actually in engineering before becoming a problem in mathematics. And then there's there are other situations, like for instance, phase transitions, when you want to study, if you have a container with I don't know, a material taking two different phases, and you want to understand how these two phases separate. And maybe the interaction between these two phases is not just non-local, it's not just local, so not just given by the surface tension, but is given by interactions among all the points. Then in this case, you would end up with something, a non-local problem. So. And then I've done also some work in material sciences, so studying what is called the Payas-Navarro model for crystal dislocation. So, this model essentially describes, so it's considered a good explanation for the plastic behavior of some metals, in the sense that if you want, for instance, to change the shape of a can or something on an aluminum foil, you don't melt it, you try to apply some external stress in order to change its shape, and this is due to small defects that may happen at the atomic level. And it seems weird said in this way, but if you somehow try to cook up a mathematical model out of a phenomenon like this, you end up with a model involving the fractional Laplacian instead of the Laplacian. And then, of course, there's plenty of literature in biology, because, of course, I mean, if you think about the way we live nowadays, we can take, well, okay, maybe nowadays is a bit different, but till 2 years ago, we could really take a plane and fly everywhere. So we really live in a world that is non-local, and that we can really make long jumps. We can't just move. We don't just move, nearby. So we can really go far away, and so one can study situations arising in biology in which one takes into account this type of non-local version of the random walk. And I've done some work with Luis Caffarelli, Enrico Valdinosci, and Edoardo Proietti Lippi recently, and also with Giovanni Giacomini. We studied some problems related to optimal foraging strategy, so the optimal strategy that animals would take somehow to hunt their prey. So there is really a huge literature in biology where the fractional Laplacian naturally arises, and the reason is that you want to take into account the fact that people or like a given species can move not just following a Brownian motion, but also performing some kind of long jumps. Okay, so but essentially, if you think about this list, the fractional Laplacian is used to model essentially two things. So long-range interactions. So I have points far away, they speak with each other. And this is taken into account using a model which allows this point to speak with each other. So I'm not putting somehow an exponential tail to my solution, because that would completely kill the possibility of speaking with each other for this point. So I would put like a polynomial tail, like the one that we have for the fractional Laplacian, and also boundary and lower dimensional effects. If you think about the Signorini problem that I mentioned, this is what happens if you don't take an n-dimensional obstacle, but an n-1 dimensional obstacle, and so you somehow reduce your problem to one dimension less in a sense. So it takes into account long-range interactions and boundary effects, boundary lower dimensional effects. And in terms of probability, so probably probabilists somehow studied the fractional Laplacian and the local operators in general, probably much before than people in PDE, so they know a lot of things about it. So in probability, the fractional Laplacian somehow describes, it's related to a stochastic process with long jumps. So again, I allow my point not to move just according to a Brownian motion, so just close by, but I allow long jumps, which are called Levy flights. And so this gives a stochastic process that gives rise to the fractional Laplacian. It also pops up if you have a classical process at discrete times. So you just look at discrete times. For instance, if you think about stroboscopic lamps, so something like that. And again, classical processes at a lower dimensional set. So we will see a picture about this that maybe is clear. So this is what I was trying to describe before. So you somehow substitute a Brownian walk, so a random walk where your particle really just move close by, with a random walk in which you also allow these long jumps. So I'm here, then I can take a direction, do a long jump here, then I can move close by, then I can take another direction and go here. So I can do long jumps. I can decide to pick a direction and do a long jump in that direction. And in this case, this type of random walk would give rise to the fractional Laplacian. And so the way one does it essentially is that one considers an integer lattice, so of a size h, and if you want to jump from a given position on your lattice to another, so from hk to hk tilde, which are two different points of my lattice, in a given time step, which has to be related to the space step, then if you assume that the probability of jumping from hk to hk tilde is somehow occurs with the probability density proportional to 1 over k to the power n plus 2s, then if you run your model and you compute your probability density, then you will end up essentially with the model involving the fractional Laplacian. And if you notice, the probability density is exactly the same kernel that we have in the fractional Laplacian, which is 1 over y to the power n plus 2s. So it has a polynomial rather than exponential tail. So if I want to move from hk to hk tilde, and hk tilde are too far away, I still can do that with some probability that, of course, decays polynomially fast. It's not, but not exponentially fast. So I'm not completely killing the possibility of jumping far away like I would do if I consider a Brownian motion. I'm putting something that, of course, has to decay, because the probability of jumping far away has to be less than the probability of moving close by. But still, I'm not completely killing that. So I would put a polynomial tail. And this is instead what I was mentioning before, that in terms of stochastic process, in terms of random walk, the long jump random walk can be seen as somehow the trace of a classical Brownian motion. So for instance, so this bit here, so the half space here is Rn plus 1 plus. And so I run my Brownian motion here in Rn plus 1 plus. And then every now and then I can hit the boundary and get reflected, and then keep moving according to a random walk again, to Brownian motion, and then I can hit again this line and get reflected. So if you see a classical Brownian motion somehow produces in one dimension less a Brownian motion in which you allow long jumps, because here, if you just look, if you forget about whatever is upstairs here, if you just look at this line, here you will see just jumps. Okay, so if you know a bit about the fractional Laplacian, this is the counterpart in probability of the Caffarelli-Silvestri extension. So that tells you that if you have a non-local problem on the trace, you can localize it by adding one dimension. And so a non-local problem on the trace with the fractional Laplacian would have a local counterpart with the Laplacian of some more general operator in the upper half space, which is exactly what is happening here. So here I'm moving according to a local process. I'm moving randomly, following a random walk, but on the trace I have I see a long jump. So this thing here would involve a non-local operator. Okay, so let me, I want to present you a result today before moving to the Malmheden Theorem that is somehow in striking difference with what happens in the classical case, that essentially tells us that up to a small error, all functions are s-harmonic, and we will see what it means precisely. But before giving you this result, I want to do a computation with you, which is essentially the computation of the fractional Laplacian of a given function. And there are a couple of reasons for which I want to do this computation. One is that I will use the fact that this function, as it is defined here, is as fractional Laplacian equal to 0 on the half line. So I will use it in the proof that all functions are s-harmonic up to a small error. And the other one is that I like this computation. So I think it's a bit long, but it's it doesn't use any complicated machinery. It's really just computing this integral, so computing the fractional Laplacian of this thing. So writing down the integral and using somehow smart, clever integration by parts. So I want to show you this proof because this also tells us how difficult it is if I want to compute the fractional Laplacian of a function instead of computing the Laplacian of the function, which is much, much easier. Like every first year student knows, computing integrals is much more difficult than computing derivatives. So this can't be easy. It's gonna be, it's gonna take some slides to prove this, but I think it's a nice and illustrative computation to do. So I think the first time that I saw the proof of this was some years ago when I was visiting Madrid, and I think we did this proof with Fernando Soria, who is in Madrid. And it was not easy. Well, you will see, one has really to be careful with integration by parts and see how things magically cancel. Okay, so this is the theorem that I want to prove. So I take a point x in Rn, and so for every point x in Rn, I define the function ws of x to be x plus to the power s. So I'm going to take the maximum between x and 0 and take it to the power s. So it's essentially 0 when x is below 0, and then it has a cusp at 0, and then it's x to the power s on the positive half line. So in dimension 1. And then, okay, so this is an operator of order 2s. And we are taking the derivative of x to the power s. So we would expect, like if we take the Laplacian, we would expect a drop of essentially two orders, right, for the function. So here we are taking the fractional Laplacian of x to the power s, which means we are computing, so we are taking somehow 2s derivatives. So we expect to have something like x to the power s minus 2s. So x to the power minus s, which is what you see here exactly, multiplied by, okay, the right constant. Now, and this is true, this actually works. So you see, you have x to the power s, to the power minus s. The catch here is that this constant is not 0 only if x is below 0, but if x is bigger than 0, this constant is 0. And this is in a sense a kind of magic for me, like it's not obvious, like I would have expected something like x to the power minus 2s everywhere. So it's not completely obvious why one should expect 0 when x is above 0. So this function is s-harmonic on the half line, x bigger than 0 in dimension 1. And yeah, we will do the proof. We will see where this comes from, and we will see it comes from some nice cancellation. But yeah, so I think it's a nice and instructive example to compute the fractional Laplacian of this object, especially if you have never seen the definition of fractional Laplacian, because then we can really understand how it works and we can appreciate somehow the difficulties that one has to deal with when dealing with the fractional Laplacian. Okay, so the first thing that we want to do, and we will see why, once we write down the fractional Laplacian of this function, I want to prove this formula here, okay? So this is like, I don't know, a calculus 1 exercise. So I have two integrals in one dimension, and I want to compute them in such a way that the sum is 1 over s. Okay, so calculus 1 exercise. It's not completely straightforward, we'll see. So this is the beginning of the computation. So I will fix an epsilon bigger than 0. So I don't want to live too much close to 0. So I will fix an epsilon bigger than 0. And let me call capital C the integral. So this is the first integral, but starting from epsilon. Okay, so I will compute this integral. And I want to prove that when I take the limit, when epsilon goes to 0, this essentially goes to 1 over s minus the other integral. This is what we will see. Okay, so now I recognize that t to the power 1 plus 2s is nothing but the derivative in dt of t to the power minus 2s up to a multiplicative constant here. Constants here are important because, I mean, we have to be precise here because we will have cancellation in the end. So we can't just say constant depending on s. Okay, and then I do my integration by parts. So this is going to be 1 over 2s, and then this function evaluated at epsilon minus the same function evaluated at 1. So this is going to be the function evaluated at epsilon, and this is going to be the function evaluated at 1. And then I have plus 1/2 the integral of the derivative of this function now times t to the power minus 2s. Okay, and then of course you can take you can do Taylor here with 1 plus 2s and 1 minus, 1 plus epsilon to the power s and 1 minus epsilon to the power s, and recognize that this thing here is essentially of order epsilon squared, because of course the order 1 is, the order 0 is cancelled by the minus 2, and the order 1, the linear 1 is cancelled because I have a plus epsilon here and minus epsilon here. So this thing, the numerator is of order epsilon squared, divided by epsilon to the power 2s, so minus 2s, which I will write like little o1, meaning that this is a quantity that will go to 0 when epsilon goes to 0. And then I keep minus 2s plus 2. And then here, two integrals. So I'll take the 1 plus t here and the 1. Okay, and then I want. Change variable in such a way that I have the same integral. So I want this changing variable. So I will call t tilde to be t over t minus 1. And then if I do.
Serena,
Yes?
sorry. I don't know if I don't listen. I don't hear very well. I mean, sometimes the it's like the sound stop. I don't know if it's my okay. So we have the same problem with David Jesus.
Okay. So you don't hear me well?
Sometimes the sound interrupts.
Okay.
Your voice. Yeah.
Yeah, I think you freeze a bit, but it's coming back, I guess.
Okay, because I had a moment where somehow the slides froze, so maybe I had a problem with the connection. But so
yeah, the last part of this slide was I think we weren't able to hear your speech, your voice in the end at the end of the slide. I mean,
slide.
This slide.
Okay,
yeah.
So
the comments you made probably we weren't able to hear to listen.
Fine. Is that okay?
Yeah, not very much. Your connection is a bit stable, I guess.
Yeah.
But it should be better now because the computer is not complaining. Tell me if I freeze. Okay, so here expansion of the numerator. So if I do the Taylor expansion of 1 plus epsilon and 1 minus epsilon, I would have an order 0, which is 1 plus 1, which gets simplified by the minus 2. The linear bit will also be simplified because I have a plus epsilon here and a minus epsilon here. So I've got something of order epsilon squared divided by epsilon to the power 2s. So I have epsilon to the power 2s, sorry, 2 minus 2s here, sorry, which I will write here at little o1, meaning that this is a quantity that will go to 0 as epsilon goes to 0. Okay, and the minus 2 to the power s plus 2 is still there. And then the second integral, so this takes care of the first bit here in square parentheses. And then the second integral, I will write it as, I will simply split into two integrals. So 1 plus t is going to be here and 1 minus t is here. And now I want to change variables in the second integral in such a way that I have the same integrand as I have here, because then I want to put these two things together. So I can do this if I set t tilde to be t divided by 1 minus t. And then if I do this, I will realize that the second integral is actually equal to essentially the same integrand function that I have in the other integral, but the two endpoints are different. So I go from epsilon divided by 1 minus epsilon to plus infinity. Okay, and so at the end of the so that stays the same. And here I have this integral evaluated here. Integrals. An integral between epsilon.
We are having the same problem.
Okay. So I think I've lost you at some point.
Yeah, now we can hear.
Yeah, sorry. I don't know what happened. Okay, let's try again. Okay, so I did my change of variable here to get essentially the same integrand, and now I'm happy because I can rewrite this difference in this way, just looking at the endpoints of these two integrals and rearranging them in a way that is more convenient, because now I want to take the limit when epsilon goes to 0. So if I do that, okay, this is nice because this does not depend on epsilon. But I have to check what happens to the first integral. So the first integral, okay, can be simply estimated by putting, so remember that s is below 1. So here I have to put epsilon if I want to do smaller or equal than, and same here, because this is decreasing now. So I have to put here the smallest one. And then epsilon, and so then this is going to be 1 plus epsilon to the power s minus 1, and then epsilon to the power minus 2s, which is here. And then I will have the difference between these two, which is an order of epsilon squared times 1 minus epsilon to the power minus 1. So essentially, this is an order, so this is a little low one. So this term here, this integral here will go to 0. Okay, so at the end of the day, Xi, so capital Xi, is going to be the first term, so the little low one is gone now, minus the 1/2, and this integral here, which was this bit here. Okay, and now I look at this one and I integrate by parts again. So I recognize that 1 plus t to the power s minus 1 is equal to 1 plus s to the power s. And then I do my integration by parts. So if I do this, I get essentially a number plus another integral. And now I'm happy because at the end of the day, I have the Xi, so the limit in Xi when epsilon goes to 0, which was this object here, is equal to minus 2 to the power s plus 2 divided by 2s, plus this last integral, which is equal to this one. And so if I sum up these two, I see that I end up with 1 over s here, and these two were exactly the first two integrals that I was summing up. So I've proved 7. So I've proved that the sum of these two is equal to 1 over s. Okay, and now I essentially claim two things, three things actually. So I will compute the fractional Laplacian of my function at the point 1, then at the point minus 1, and then I will claim that essentially this is enough to check the fractional Laplacian everywhere just by nice scaling properties. So once I know the value at 1 and at minus 1, I'm done with all the points. Okay, so this is my claim now. So let me make a couple of observations, and then we will write what the fractional Laplacian is. So let's just notice that this function here is even. So if I switch t with minus t, I will get the same. So the integral between minus 1 and 1 of this even function is just twice the integral between 0 and 1. And also we will have something between minus infinity and minus 1, which again, I can switch variables, switch from minus t to t, and get an integral from 1 to plus infinity of something. And the reason why I want to do this computation is because if I write down the fractional Laplacian of the function ws evaluated at 1, well, this is the integral in R. We are in dimension 1 now. So this is an integral from minus infinity to plus infinity of ws 1 plus t plus ws 1 minus t minus twice ws of 1. And then, of course, WS is the positive part to the power S. So I will split this integral into 3 bits. So the integral when t is below -1, and then when t is in between -1 and 1, and then when t is bigger than 1. Because when t is below -1, this one here will be 0. So I will just end up with 1 minus t to the power s, and then this is the positive part of 1 to the power s, which is just 1. So I will get a -2 here. And then same here, just that I have the three of them. So it's 1 plus t to the power s plus 1 minus t to the power s minus 2. And then from 1 to plus infinity, I don't have this one because 1 minus t is now negative. So this is 0. So I've got just the first and the last one. Okay, and now you understand why I wanted to do the computations in the previous slide, because this is going to be twice the integral between 0 and 1. And in this one, I will do the change of variable, switching minus t into t, and I will end up with essentially the same thing that I have here. So this is going to be twice this object. And now this is twice that can be put as a common factor. And then I have, if you remember, this is essentially, this is xi plus this integral, and then minus, this is exactly what I called xi. And this second integral can be split again. So I have 1 plus t to the power s, which is here, and then the -2, which is here. And then I know that capital Xi plus this object was 1 over s. That's the first computation that I did. And then I have -2 this integral that I know how to compute. So this integral is simply 1 over 2s. So at the end of the day, this integral is 0 because I have 1 over s minus 2, 1 over 2s, which gives me 0. So this is 0. And this was exactly the fractional Laplacian of Ws at 1. So I know that. So I know that if I take, if I look at 1, the fractional Laplacian is 0. Okay, what happens instead at -1? At -1, I can write down Ws minus 1 plus t plus Ws minus 1 minus t minus twice Ws at -1. Now, these two objects can be written here. So this is the positive part of the power s of the argument here. And this is the positive part of -1, which is 0. So this term is not there. And this is bigger or equal than 0. So this is not identically 0. I will have some mass somewhere. And so I will have that minus the fractional Laplacian to the power s, the fractional Laplacian of Ws at -1, it's some positive object. So it's strictly bigger than 0. Okay, so it is 0 at 1, and it has a sign at -1. And now the last claim is that this is enough to complete the proof, because now it's just a matter of rescaling. So now let me use this notation. I will let the sigma to be either +1 or -1, depending on the sign of a fixed x. So I will fix an x in R. If x is positive, sigma is +1. If x is negative, sigma is going to be -1. Okay? And then my claim is that, okay, if I do Ws of sigma multiplied by 1 plus t, this is exactly as doing Ws at sigma plus t, and same here. And again, this is just a matter of checking. Of course, if x is positive, then sigma is equal to 1. This is exactly the same thing. I'm not doing anything. But if x is negative, so sigma is equal to -1, and I change variable, I call tau to be -t, then I can essentially prove it, because now, so now if sigma is equal to -1, this is -1 minus t, and this is -1 plus t, and then I change variables, so I call -t to be equal to tau, so this becomes the second last integral here, and then this is exactly, sigma is -1, so this is exactly sigma plus tau, and then sigma minus tau. And this proves this thing. Now, this is an intermediate step towards using the scaling properties. So now we use a scale argument now. So notice that Ws evaluated at norm of x multiplied by r, so absolute value of x, we are in dimension 1 here, multiplied by r. This is xr plus to the power s. Now x is non-zero, so this is x to the power s, and then r plus s, which is x to the power s, ws of r. So ws is has some homogeneity. And so if I write now xr as sigma, so the sign of x multiplied by its absolute value, I can take x to the power s outside, and this is ws of sigma r. And now you understand why I want to use the computation in the previous slide. Because now, okay, I have to evaluate the fractional Laplacian at any point x. So I will do this change of variable. I will call y equal to be tx. So t will be my new variable. So I do this change of variable. And then you see, I use the homogeneity of ws. So I will have, so I have an x to the power 2s in the denominator coming from the change of variable. And then I use the homogeneity. So here I will have x to the power s coming out, which in total will give me an x to the power minus s, which is what we wanted. And then I have this object here, which is nothing but, if I use this computation in the previous slide, nothing but the integral of ws sigma plus t plus ws sigma minus t, and so on. And so basically, this means that the fractional Laplacian at any point is nothing but a rescaling of the fractional Laplacian at -1 if x is negative, and the fractional Laplacian at 1 if x is positive. So at the end of the day, because we already proved that the fractional Laplacian at 1 is 0, this is going to be 0 for any point positive, for any positive point. And because we know that this object here is a positive constant, oh, sorry, a negative constant, because it was minus, it was positive. So this is a negative constant, but different from 0. Then I have that the fractional Laplacian is equal to x to the power minus s multiplied by some negative constant. And so this basically proves our result. So this function x plus to the power s is s-harmonic in the half line. So the fractional Laplacian of this object is 0 in the half line. And now I think you can appreciate the difficulties that one has to deal with when one has to do computations with integrals. So we did an easy computation with some kind of nice and homogeneous function in dimension 1, and we had to fight a bit to recognize the right cancellation with integration by parts. Now, of course, one can do the same computation in higher dimensions. So if one defines for every point in a Rn, I don't know, x, the function x1 plus to the power s, one can essentially do the same computation, and this function would be s-harmonic in the upper half space. Because one can check that if you want to compute the fractional Laplacian of a function that is defined in a Rn, but is actually one-dimensional, then the fractional Laplacian in n dimension will be some kind of constant multiplied by the fractional Laplacian just in the direction that your function depends on. So one can essentially, from here, from the one-dimensional computation, one can basically obtain the computation also in higher dimension. Okay, now, is everybody still there? So can you hear me well?
Yes, yes.
Okay, good.
Sure.
Okay, so I thought it was nice to show you this computation because we are going to use this function as some test function in the proof of the next result, and I think it's a nice computation to see. It's kind of easy once you see it, but I mean, if someone does it for you, it's kind of easy, but otherwise it's not completely straightforward to recognize all the possible cancellation and simplification that one has in the integral. Okay, so now I want to prove this theorem that sounds quite wrong if you look at it. So here on the top of this slide, so I claim that all functions are s-harmonic. Okay, and I should put up to a small error in parentheses, but allow me at this time of the day to be a bit sloppy. So first of all, I will say that U is s-harmonic in omega if the fractional Laplacian is equal to 0 in omega. And then this sentence here, so these words here mean that an arbitrary function can be approximated arbitrarily well in a given ball by functions whose fractional Laplacian vanishes in such ball, in sharp contrast with what happened in the classical case, in which harmonic functions are somehow more rigid. So if you think about dimension 1, harmonic functions in dimension 1 are straight lines. And it's not true that I can approximate any function in dimension 1, so as wide as you like, with the straight line. This is a false statement, and similarly in higher dimension. But if we go to the non-local case, to the non-local scenario, this may happen. So close to any function defined in a given ball or in a given domain, I can find close to this function another one which is now s-harmonic in the one. So this is completely different from what happens in the classical case. So this is not that we are just trying to redo a theorem that is true in the classical setting, also in the local setting. This is completely different from the classical case. And so this is the exact statement in mathematical words. So I fix a k, and then for any function in the ck of B1 and for any epsilon, I can find the radius r epsilon and the function u epsilon in the right energy space, such that this function u epsilon is s-harmonic in B1. So its fractional Laplacian is equal to 0 in B1. U epsilon is equal to 0 in Rn minus this Br epsilon, so it's compactly supported. And the important thing is that this function is close to your original function in a kind of strong norm, in the ck norm, so very strong. So now the problem is not really how do you prove it, but it's really how do you think about something like that? Because again, this is a result again that we kind of stumble into because I remember we were trying to construct some barrier for some free boundary problem or something like that. And at some point we realized that, okay, all functions are s-harmonic, and in principle we thought, oh, no, it can't be true, because if this thing that we are doing at the blackboard is true, then this means that all functions are s-harmonic, which can't be true because it's not true for harmonic function. But then you think about the picture. So suppose that this thick red line is the ball B1, so minus 1, 1 in dimension 1. Take your favorite function, take, I don't know, this red parabola, okay? And now that is defined in B1, nice and smooth. Okay, now change it a little bit with with another function, like the blue one here, which is, say, epsilon close to my original red parabola. Fine. Now, this satisfies the last condition here. So it is close to my original function. But now I want to make it s-harmonic. So what do I do? Well, it is a non-local situation, so I can actually play a bit with my functions outside, with oscillation of my function outside, in order to make it s-harmonic in B1. So my final function would be something like this. And of course, I don't have really control on this oscillation. So I don't really know how to construct this function. We will see the proof is not constructive. So I can't, we tried a bit, but we couldn't, we didn't succeed. So one does not have an explicit construction in the proof. The proof we'll see is by contradiction. And the reason why we don't have an explicit proof is because this would really mean deeply understanding the oscillation, so the role of the oscillations, so the role played by the oscillations in the definition of the fractional Laplacian. So this would really mean that we can do whatever we like with the object. We can construct all possible barriers, all possible functions that we like, which is a difficult problem. So computing the fractional Laplacian of functions is a difficult problem because, we have done it for some kind of easy function. It was already tricky enough. And understanding the how possible oscillations, possible modifications of your function somewhere affect the computation of the fractional Laplacian is, I think, a deep problem and is very difficult. And so this would be really a striking result. If one really managed to construct this function, that would be, I think, an important result, not only per se, but because that would mean that essentially we can compute the fractional Laplacian of functions because we know what's going on there. Okay, so this is the idea, and this is why at the end of the day we were convinced that a statement of this type can be true in the non-local setting and cannot in the local one, because there's no way that you can play with things outside your ball to make your function harmonic inside. There's no way that you can do that, but you can do for the fractional Laplacian. And so we decided, okay, let's try to give a proof of this result. And I will give you a sketch of the proof. This is, again, it's a simple proof once I will show.
Serena, sorry, can you go back to the statement?
Yes. Do you have questions?
No, it's fine. Thank you.
It's fine. So given a function, given epsilon, I can find a radius and a function that is s-harmonic in B1, 0 outside some ball, and it is close to my function in the CK norm. Now I will be a bit sloppy, so I will drop this thing because one has to play a bit, just a technical detail, but I will show you how one can prove that you have an s-harmonic function close to your original function. So this is the heuristic motivation for which one can think that this type of result is true. Let's try to do the proof. The proof is essentially in 3 steps, we will see. And the first one is, okay, use Stone-Weierstrass theorem. So by Stone-Weierstrass theorem, okay, it is sufficient to prove the result for polynomials because every CK function can be approximated by polynomials in the CK norm. Okay, so from now on, I will suppose that my function is a polynomial of this type, x to some power beta divided by beta factorial. Okay, let me put beta factorial because then when I will take derivatives, I will get simplifications in the constant here. Okay, so I will, and beta here is a multi-index. So x to the power beta is x1 to the power beta 1, x2 to the power beta 2, and so on. Okay, so this is the first step. Okay, so from now on, u of x is a polynomial. And then the second part is really the core of the proof. And one can prove this, the following core lemma. So the idea is that I can span the derivative, the space of derivatives of a function in this way. So the core lemma tells us that I can find a function v such that this function is s-harmonic in some given ball, Br, for some r. All the derivatives up to order beta minus 1 are 0, and they are also 0 when the order is beta, but the multi-index is not beta. And then the only derivative that is not 0, that is 1, at 0, is the beta derivative. And that's, now you understand why I wanted to divide by beta factorial, because then I can say that the derivative at a given point is 1, is not beta factorial. So this is a strong result, and I think it's interesting per se, because this is saying that I can construct an s-harmonic function, so at least not that I can construct, there exists an s-harmonic function in a given ball Br, for which I can write the Taylor expansion up to a given order. Okay, so I can prescribe derivatives up to order beta, and this function is s-harmonic. So this is a relevant result, in my opinion, per se. And this is where we can't really construct this function. We know that it exists. So how do we do it? Let me show you the proof, because this is one of my favorite proofs. So I really want to share this with you. So let's just do the proof in one dimension, simply because, I mean, the proof in higher dimension is the same, just that I have partial derivatives and I don't want to deal with multi-indexes and stuff like that. I just want to have one index. Okay, so let me call zeta to be the set of functions that are s-harmonic now in minus r. So this is my BR in dimension 1 for some r, okay? So zeta is the set of all the functions that are s-harmonic in some ball centered at 0, or in some neighborhood at 0, if you prefer. And then for any v in this space, for any v s-harmonic in V1, in BR, so at any v, I associate a vector in r beta plus 1. Oh, sorry, this is not k, this is beta. Anyway, so this vector matcal d beta of v at 0 is the vector which consists of v of 0, first derivative of v of 0, second derivative, beta derivative. So this k is a beta, actually. A beta is just a natural number here. This is a vector in r beta plus 1. So to any function in zeta, I can associate a vector in r beta plus 1. And then I call V to be the vector space spanned by this construction. So V is the subset of r beta plus 1 that is made of all these possible vectors that come from s-harmonic functions in some ball. And V, okay, can easily check that V is a subspace over beta plus 1, is a vector space. The final claim is that V is actually r beta plus 1. It coincides with r beta plus 1. If I prove this, I'm done, because then r beta plus 1 essentially coincides with the space of all vectors done like this. So for instance, the vector...
Serena, can I ask you, beta is multi-index?
No, beta here is, sorry, I should have changed the notation. Beta here is just a natural number because we are in dimension 1.
Okay,
so you are in beta
exactly.
derivatives.
Yeah,
so this is a typo.
No,
this is
a
typo.
It's fine.
This case is beta, okay? So
yeah,
mistake.
beta is k.
I had in mind one dimension and I didn't want to change the notation.
No, of course, sorry.
Okay. Okay, so this is, of course, if you are in higher dimension, again, you have a vector, but a vector in R to some power, okay? But this because you have to take into account all possible partial derivatives. But just to make the story simple, I decided to do it in 1D. Okay, so if I prove that V is actually R beta plus 1, then of course I can take the vector 0, 0, 0, 0, 0, 1. That belongs to r beta plus 1, but also to V. So I will have a function V s-harmonic for which the derivatives are 0, 0, 0, 0 up to beta minus 1 and then 1, which is what I want to prove. I want an s-harmonic function with all derivatives up to beta minus 1, 0, and then beta derivative equal to 1. So this is my claim. This is what I want to prove. So let's prove it by contradiction. So that's why we don't construct it. We will prove it by contradiction. So we suppose by contradiction that V is a proper subset of r beta plus 1. So I can find another vector not identically 0 that is orthogonal to any vector in V. So such that the scalar product between C and this d beta V of 0 is 0. And so the scalar product is this, with the product of the components summed from 0 to beta. So this is 0. Okay, and now the core here, the gist here is that I want to choose like the right function V, the right s-harmonic function V, in order to get to reach a contradiction. So which one should I choose? Well, we've just done some computation. So I will take V to be x plus some eta. Eta is a positive small number plus to the power s. I want this because if you remember, x plus to the power s is s-harmonic when x is bigger than 0. I want something that is s-harmonic in a neighborhood of 0. So I will have x plus eta. So this is going to be s-harmonic when x is bigger than minus eta. In particular, it will be s-harmonic in minus eta. So this function lives in my space V. So I can plug it here. And then I will get that 0 is equal again to this sum. And then I have to compute the derivative of this object. So these are the jth derivative will be s times s minus 1 times s minus 2 up to s minus j plus 1. And here I will have, of course, I will have x plus eta to s minus j at 0, evaluated at 0. It's going to be 8 eta to the power s minus j. Okay, and then I can take eta to the power s outside of the sum, and I will end up with this. And then I will call t to be 1 over eta, because I don't like that I have eta to the power minus j. So t is 1 over eta. So this is going to be, so this becomes 0 equal to this sum of some coefficients t to the power j. So this will be a polynomial in t, defined in some subspace over R, some open set, sorry, of R. We are in R here. Okay, so then I use the identity principle of polynomials, which means that all the coefficients here have to be 0. So for every j from 0 to beta, these coefficients have to be all 0. Okay, and now it comes the fact that s is not an integer. So s is not 0, s minus 1 is not 0, s minus 2 is not 0, s minus j plus 1 is not 0. So none of these coefficients can be 0, because s is not an integer. So bottom line is that Cj, all the Cj's, all the coefficients have to be 0 for every j from 0 to beta. And this is a contradiction, because we assume that C was a non-trivial vector, so it can't have all the coefficients equal to 0. So this proves that V is equal to R beta plus 1, and so I can actually span R beta plus 1, R to the power beta plus 1, using derivatives, vectors made by derivatives of s-harmonic function. And in particular, 0, 0, 0, 1 is a vector in this space, so I have my function. And you see, this is the thing that would break in the classical case, because here, we strongly use the fact that s is not an integer. But in the classical case, I would have an integer here. So this proof wouldn't work, and that's the reason why it wouldn't work, because the final result is not true. Okay, and now with this we are essentially done, because now I have my function v, which I like, because, so remember, we started with a polynomial x to the power beta divided by beta factorial, which has all the derivatives up to order beta at 0, 0, 0, 0, and then 1, the last one. So I have constructed an s-harmonic function with the same derivatives up to order beta as my polynomial, right? So up to beta, I am fine, I'm happy. But say that I want to prove that my theorem is true in CK, I want to make all the other derivatives small, right? All the other derivatives of my function v small. And how do I do that? Well, here now it's just a matter of rescaling. So I have my function v. V is my function given by the core lemma. And I just rescale it. So u epsilon of x is going to be v of epsilon x divided by epsilon to the power beta. So this is again the length of beta, because I'm assuming that I am in every dimension here. And now let me recall that, as I said, v of x was x to the power beta divided by beta factorial, because I know the Taylor expansion of v up to order beta, so it's like this, and then I have smaller order terms. Okay, so with gamma, a multi-index which is whose length is bigger than the one of beta. And then I have that what? So u epsilon, this is going to be my good function. So u epsilon is by definition v of epsilon x divided by epsilon. Oh, sorry, this is this should be the length of beta. Sorry, here. And okay, but now I use this Taylor expansion here. So V of epsilon x, so V evaluated at epsilon x is going to be epsilon x to the power beta divided by beta factorial epsilon to the power beta plus some order, lower order term. And here you see epsilon to the power beta gets simplified in the first term. So I'm not changing, I'm not spoiling all the work that I've done for the derivatives up to order beta, but I'm gaining something for the rest of the derivatives. So here I will get something of order gamma minus beta, which is positive, so something smaller. So I basically, with this rescaling, I have not spoiled the work that I've done up to order beta, but I've made all the other derivatives small. And so this is basically what I want. So this part is a bit sketchy. Of course, one has to be a bit careful with things, but the idea is this one. So once you have fixed what happens up to order beta, it's just a matter of rescaling in order to make to keep the derivative up to order beta there and make all the other derivatives equal to 0. Sorry, small enough. So this completes the proof of this result. So as you can see, it's not constructive. We don't have an explicit construction of this function. And the point is that the core lemma is not constructed. We can't construct that function with a given Taylor expansion up to a certain order. Okay, so I think I will start talking a bit about the fractional mean value theorem, since this was the core of this course, together with Malmheden Theorem, and then probably I will continue tomorrow. So we have seen up to now some properties of these s-harmonic functions. We have understood that the global picture plays a role, so we have to understand the global picture if you want to understand harmonic functions. And something that is also a bit different from the classical case is also the fractional mean value theorem. So also in the non-local scenario, you can characterize s-harmonic functions with a mean value theorem, with a mean value formula that is slightly different from the classical case. So this theorem here can be found in Lankoff book, so it's not something that we discovered recently. It's, I mean, people knew probably all these things. I mean, they have been working on this type of operators since a long time ago. So here is the characterization. So a function U is s-harmonic in some ball if and only if for every ball of radius small r containing the R, U0 can be written in terms of the value of the function, now not on the boundary of the ball, but on the complement of the set. And all of this has to be weighted with some kernel. And then I have a constant in front that depends on n and s, but for me n and s are fixed, so I'll just keep, I mean, I will forget about this constant at the end of the day. So you see, there is already a difference with the classical case. In the classical case, if I want to solve a Dirichlet problem, I take, okay, an harmonic function in some ball or in some domain omega, and I have to give the value of the function at the boundary of the ball or of the domain or whatever you have. Here, because I have to define the function everywhere, okay, I can define my problem as fractional Laplacian of U equal to 0 in some ball, but then it's not enough to say what this function is on the boundary of the ball, because the fractional Laplacian sees the values of the function everywhere. So I need to define the function everywhere. So the boundary datum is somehow replaced in a local setting with an exterior datum. So my problem would be something like fractional Laplacian equal to 0 in V1, and then U equal to some f or whatever in Rn minus B1. So the boundary datum is not enough. I have to define the function everywhere in the complement. And so this thing, I mean, we can see this thing also in the fractional mean value formula, because in the classical case, we would have u of 0 equal to the average of the function u on the boundary of BR. So here we have to take not the boundary, but the complement of the set. We have our function u, and the other difference is that we don't have only the function u, but also a kernel. And this makes sense if you think about the probabilistic interpretation of harmonic and s-harmonic function. So essentially the idea when you solve, I don't know, a Dirichlet problem with the Laplacian is that, okay, I have my particle moving in my domain with a random walk, and the game that I play is that, okay, if I hit the boundary, I get a payoff equal to f, which is the boundary datum, okay? So I really I can hit the boundary and I get f. In the non-local setting, where I also assume that I can jump far away, I move around, but I can also make a long jump, not hitting the boundary, but I can jump outside. So first of all, I have to define my function everywhere, and this is something that we already discussed. But second, the probability of jumping depends on where I'm jumping, right? So the probability of jumping was something like 1 over x to n plus 2s, to the power of the fractional Laplacian, right? So the probability of jumping far away has to be less than the probability of jumping close by. So the payoff, in a sense, has to see this difference in terms of probability. So it has to have some kind of weight. So we can expect that here we don't have just a function u, but also some kind of weight that tells me, okay, it's more probable to end up closer to the domain than farther away. So heuristically, we can expect something of this type. And then, of course, understanding which type of kernel, then, okay, you need Lankov and you need to do the computation. But the idea that you have a kernel which is integrable, because so at infinity, this goes like y to the power n plus 2s, so it's integrable at infinity. So under some reasonable assumption of the function u, this object will be finite. And it is also singular when y is equal to r, but the singularity is over the rest, so again it is integrable. So this object, if u is reasonably nice, is a nice and well-defined object. Okay, and then one can play some games here, in the sense that, okay, we have a fractional mean value theorem, so we can characterize a harmonic function. Can we have also a current type theorem? So can we characterize domains which satisfy a fractional mean value theorem? So there is an answer here, which is not completely satisfactory in my opinion, but I mean, it's not an easy task to deal with, because if you can see here, the fractional mean value theorem sees the balls. So if I want to say, okay, I have a ball at the end of the day, well, this formula, the kernel that is inside this formula sees the fact that I have a ball. So which type of kernel should I put here? Should I already start with the same kernel? This is not clear. Or, I mean, we will see, we will discuss it a bit in detail. But so to simplify a bit the notation, one can write this kernel, one can put it all together, and instead of having the kernel with dy, one can interpret this object using a probability measure on Rn minus Br. So one can call this object d mu r. And then one can simplify a bit the notation to make the fractional mean value theorem more similar to the classical one, where I have just u here integrated over the complement of Br. But the kernel, the kernel is hidden here in the measure, which depends on R, depends on the ball number. And so one can prove some kind of inverse theorem in the spirit of the one proved by Courant. And this is something that we worked on with the Claudia Bucur and Enrico Valdinoci. And the result that we finally managed to prove is the following. So I have a domain, a bounded open set containing the origin, and say r is the distance between the origin and the boundary of omega. And then suppose that I can write for all s-harmonic functions u in omega, u of 0 to be the integral over Rn minus omega of u of y in d mu r, y. And then I have to take the average, essentially, so I will divide by the measure that I have here at Rn minus omega. Then, if I have this type of fractional mean value formula, then omega has to be the Bohr, okay? So in short, if omega satisfies some kind of fractional mean value property, with respect now to a suitable measure, then omega is necessarily a Bohr. Yeah, so I will not start the proof of this theorem because we have done a lot today and we are all a bit tired. But let me mention that the reason why I'm not completely, I'm not very happy about this theorem is that, okay, we are kind of assuming that the measure that we are dealing with is the one of the Bohr, though we will see it's not completely straightforward to prove that in this situation omega is the Bohr PR. I will show you a couple of proofs tomorrow. None of them is completely straightforward. So it's not that because, okay, oh, I write down the measure of the Bohr, then it has to be the Bohr. It's not completely easy. There's a bit of tricks that one has to do. On the other hand, it's difficult to imagine another measure here because then it's not clear if I put a general measure here, what can be done, because that can be related also to the balayage problem that Poincaré dealt with at some point, where you can prove something like this with for a general domain, where you put like what is called, I think, the harmonic measure or something like this. So it's not completely obvious that one can really prove something more general, so with a more general measure here. So I think tomorrow we will restart from here and we will see a couple of proofs of this result. So again, none of which is completely obvious. So they both requires a bit of work to be done. And then we will move to Malmheden Theorem, because once we have the fractional the fractional mean value formula and the fractional Coulomb theorem, of course, the next step is trying to understand whether the geometric construction can be also translated into the non-local scenario. So I will stop here for today, and sorry for the inconvenience with the connection. And thanks for listening till now.